Okay, so suppose we have two sequences, okay, A sub n and B sub n, such that every element in this sequence A sub n is smaller or equal than the elements in B sub n, okay? And both sequences are positive or greater than 0, non-negative, right? Then the series that we get by summing the terms in the sequence, okay, remember the difference between a sequence and a series, which is a sum of terms of a sequence. Well, if the series of B sub n, of the terms of B sub n, which is, the term B sub n is always greater than A sub n, if this sum is convergent, smaller than infinity, then it means that the sum of the terms in A sub n, that series associated with the sequence, is also convergent. And alternatively, if the series of A sub n is divergent, I mean it goes to infinity, then it implies that the sequence, the sum of the terms of the sequence B sub n will be divergent as well. Okay? So the proof for this is easy, which means it goes like this. The sum from n equals k1 to k of A sub n, well, this is smaller than the sum from n equals 1 to k of B sub n, right? Because every A sub n is smaller than B sub n, right? So if you have A sub 1 is smaller or equal than B sub 1, and A sub 2 is smaller or equal than B sub 2, and so on and so forth up until B sub n. Well, if you sum all of these parts of the inequality and you sum all of these parts, the result is still an inequality. Okay, that's what we're saying here. Okay, up until A sub k and B sub k, sorry. Okay, well, now this is by definition smaller than the sum from n equals 1 to infinity of B sub n, because every term in B sub n is positive. Okay, so if you sum more terms, this will be greater. Okay, at least. Now, starting from the first assumption, okay, if this is, we assume this is convergent, that is, this is smaller than infinity, then this thing will be smaller than infinity. Okay, so the sequence of partial sums related to A, so for instance this is, call it A sub k. A sub k is bounded, is smaller or equal than some value b, which is the value of the series. Okay, if we call b is equal to the sum from n equals 1 to infinity of B sub n, okay, this is the value of this of the series, then every partial sum A sub k is bounded by B. Okay, so this is this here A sub k is a sequence here of increasing terms, we just said, and it's bounded above by B, by capital B. So that means this thing will have a limit. Okay, so that's the implication. The sum here will be smaller than infinity. Okay, now also if this sum, alternatively, if this sum is infinity, then that means that this how to say this, as we keep increasing this they take the limit, this goes to infinity. So this series and this one is greater, sorry, so we're in the second part now. Okay, if we take the limit from, when k goes to infinity here, this will be smaller than this, smaller or equal than this. But if this is infinity, then this has to be infinity as well. So that's the proof, right? If this is divergent, then also this is divergent. Okay, and intuitively it makes sense, right? If all the terms in B sub n are greater than the terms in A sub n, and you sum this, all of this, and you get some real number, then it makes sense that when you're summing things that are smaller than this, you will also get a real number. And if you sum something that's very small and you get something that's infinity, when you sum something that's greater than the thing that is infinity, when you sum it, it makes sense that you will get infinity as well, right? Or not any, you don't get any convergence. So yeah, so the theorem says that this condition has to be true for all n on all natural numbers. But this this doesn't have to be true. Okay, it's a very strict condition. But you could relax it and say, well, it could be that this thing is true, but for all n greater than some value n. Okay, some natural number, capital N. Why is this so? Because as we have seen before, if we take any finite number of elements in a series and we take them out of the series, they don't really matter for the convergence of the series, right? Because it's just a finite number of terms. So if you have, for instance, a sub 1 plus a sub 2 plus blah 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 plus a sub n, and then a sub n plus 1 plus a sub n plus 2 and so on and so forth, right? And then you have b sub 1 plus b sub 2 plus b sub n plus b sub n plus 1 plus blah blah blah. Okay. Well, we don't care about these terms, okay, these terms will be equal to something. Let's call it a sub 1, and these terms will be equal to something. Let's call it b sub 1. Okay. Well, starting from here up until the infinity, then we have that a sub n is smaller than b sub n, right? This is a rule that we got. Then we can apply, starting with this series, starting with sequence starting here, we can apply this theorem. Okay, and then so if this sequence is convergent, then the whole sequence will be convergent, because for instance, if this starting in b sub n plus 1 is equal to b2, then the whole series will be b1 plus b2, right? And then we know that this sequence will be also convergent. Okay, do you see? Okay, so I'll leave you with two exercises to apply this test. The first one is to show that the sum of 1 over n factorial from n equals 0 to infinity is a convergent series by comparing it with the geometric series. Okay, and well, if you're wondering about n equals 0, the definition of 0 factorial is 1. Okay, this is just a convention. Okay, don't worry too much about it. And the hint is to note that n factorial is greater than 2 to the n for n greater than 3. Okay? And the second exercise is to show that the sum from n equals 2 to infinity of 1 over the logarithm of n is infinity, comparing it with the harmonic series.